In this second video for 9.8 and 9.9, still looking at power series. I call this one actually fun with power series, right? What we're going to do is still kind of talk about interval and radius of convergence, but also maybe what happens if we start to think about these things as functions. And what we know about geometric, the sum of a geometric series, that first term divided by 1 minus the common ratio, how that's going to show up when the common ratio is a variable. And maybe then how do we write some functions as power series and getting onto a larger concept that way. So what I've got for you here is just a general power series for x to the n there. I have n starting from 0 and going to infinity. There's no a sub n. Again, this is just kind of a 1 out front. And what we know from before is that this power series converges on the interval from -1 to 1. Again, I don't really need to check the endpoints here because if x is -1, I have -1 to the n, and that's just alternating forever. It diverges. Nothing happens exciting there. And when x is 1, I have 1 to the n. That's just adding 1 over and over and over again. That, of course, diverges as well. However, what if I want to write this? Of course, it's the sum of powers of x forever, right? What if I want to write that as a function of x? Okay, and think about being able to plug in values into that power series. Okay, similar to the previous video, that function, that power series, is going to converge only for some of these values of x. If I were to take f of 2, I would have the sum of 2 to the n. And we know that diverges because that common ratio is larger than 1. So we've got this function now that's based off a power series that only converges for some values of x. Right? And this is why we want that kind of third convergence case, right? Where we want the power series to converge for all x, then we can write it as a function for all x. But slow my roll. What we've got here, I've got a function written as a power series. This function has a domain, and that domain is exactly the interval of convergence from -1 to 1. All right? That's it. This function I can write as a power series as long as x is between -1 and 1. Okay? Now, in general, that's going to be the case, right? We say we can write functions here as power series where the domain of the power series, of the function even, is the set of x's for which the power series converges. Okay? Again, this is really just the interval of convergence. So this is why it's important to be able to find an interval and radius of convergence. As we're writing these power series as functions, that's going to be the domain or the set of x's for which these functions exist. Okay? And I want to do a couple examples with this. First off here, basically what we've got is a function written as a power series. And what I want to do, because we know about geometric series, what we can do is write this function really as the sum of that geometric series as long as it converges. And if you remember, this sum is really 1 over 1 minus x, as long as x is less than 1, right? That was true for having a geometric series involving r, right? Now I just got x. In general, this is a little bit more, complicated, but what this will do is hopefully provide us with a template to find power series of kind of a bunch of rational functions. So what we've got here, we can use this template from the general geometric series case to write all sorts of rational functions as power series. Rational functions and specifically kind of geometric power series. We don't really classify power series as geometric. And I want to do a couple examples here, just two quick ones. if I were to just change this a little bit here and say I wanted to write 1 over 1 plus x as a power series, all I've got to do is kind of rewrite things so that it resembles this template I've got up here. So what I do is I just take the denominator there and write it, instead of 1 plus x, as 1 minus a negative x. And that negative x is now going to be like my common ratio. Okay? So working backwards, knowing what I know about the sum of a geometric series, I can say that this fraction is equal to the sum from 0 to infinity of that, in blue, that common ratio minus x to the power n. I can write that rational function as a power series as long as that power series converges. Okay? Now, often you'll see things kind of written a little differently. You'll see some simplification, I guess. And what they'll tend to do is split off that alternating part, because really what I can do is say minus x to the power n is minus 1 to the n times x to the n. It's just a slightly different way of writing things. Both forms kind of have their purpose, and I'll try to outline that later. So as long as minus x is less than 1 in absolute value, I end up really here with the same interval of convergence I have before. But it's important to know that as long as x is less than 1 in absolute value here, I've got a convergent power series, and I can write this fraction as this power series, or this one. Okay? Another quick example, let's do something a little bit more challenging. Take 4 divided by x plus 2. And I'm going to write that as a power series. Okay? What I need to be able to do is kind of apply that template, right? I want to make that look like 1 over 1 minus x. Okay? The 1 on top doesn't so much matter. That's like our first term, if you remember that formula. So the 4 up there might change, and it's okay if it does. It doesn't really matter what that number is. Really what we need to see is something like 1 minus the common ratio in the denominator. So I'm going to move around this denominator a little bit and rewrite it as 2 minus a negative x. Okay, I'm almost there. The only thing else that needs to happen is that this 2 can't be a 2, it's got to be a 1, right? So what I do is I factor out that 2 from the denominator. So I take a 2 out from 2, leaving me with a 1 minus a negative x, but there's no 2 to take away from x, so I have to divide x over 2. Still a 4 on top. And what I notice is that 4 divided by 2, I can cancel those, and really all I've got left then is 2 divided by 1 minus a negative x over 2. This is exactly the form that we see the sum of a convergent geometric series, right? The first term divided by 1 minus the common ratio. So when we write this as a power series, then what we see is sum from 0 to infinity of 2, that first term, that's like our little a, times minus x over 2 all to the power n. And there you've got it. You've got the power series for 4 over x plus 2, and we did it with a little, like I said, reverse engineering, right? Working backwards, because we know the formula for the sum of a geometric series. Again, this is only true on the interval of convergence, right? So I take this minus x over 2, and that has to be less than 1 in absolute value, okay? What does that mean for x, just x by itself? Well, I can move out this minus 1/2, apply my absolute value, and I'm left with minus a half times absolute value of x, or absolute value of x is less than 2. So our domain is really from minus 2 to 2. It's within the window as long as x is less than 2 in absolute value. Okay? Those are the x's for which I can write my rational function as its power series. Okay? Now, some of the cool part about this, and what I still want to be able to do here is apply some calculus concepts, right? I want to be able to write power series, functions as power series, and then also to be able to take derivatives and antiderivatives. And of course, there's a theorem for that. What we have is theorem 9.21. We can take derivatives and antiderivatives of power series. Derivatives and antiderivatives of power series. And this is how we do it. If a function is written as a power series, and I have to use the general form here, as long as this guy has a radius of convergence of r, which is bigger than 0, then on the interval of convergence, we say c minus r, c plus r. F is continuous and differentiable, and I can find derivatives and antiderivatives. Okay, so there's two things to this theorem here. One is the derivative, the other is the antiderivative. So again, this is the general form of my power series. And I think it helps to write out these terms, what you're actually working with, right? It's like a0 plus a1 times x minus c to the first plus a2 times x minus c squared, so on and so forth. That's what my power series looks like written out. That's an A. I'm going to take derivative and antiderivative of that there in red, okay? But what we do is we're able to write it in general in the form of the summation, okay? So first, the derivative, f prime of x, right? I take a derivative of each term. The first one goes away, right? A0 is a constant with respect to x. So when I take a derivative, that constant goes away. So really what happens is we're going to start with the first term now being when n is 1. So that's the first difference we see with the derivative. That constant term that's going to be in our original power series is always going to go away when we take a derivative. And thus I can start my power series now starting at 1 instead of 0. It's not a big thing, but it's one of the first changes we see. I also see when I have powers of x minus c, the power for every one of those factors of x minus c is going to decrease by 1, right? And the original power is going to come down in front. So what I have is this n up here is going to come down and multiply a sub n times x minus c, subtract 1 from the power n minus 1. That's going to be the derivative of a power series, right? And it's really pretty easy, right? I took this n here and I brought it down in front, and I subtracted 1 from the power, okay? Very similar, I can take an antiderivative, and it's just as follows. The integral of f of x dx. What we need for an antiderivative is, of course, a constant of integration. Let's get that out of the way. We have a c plus. I'm going to add a constant when I take an antiderivative, right? Plus, I still have my series. Again, I don't switch from 0 to 1 in this case, right? There's no real shifting that needs to take place as it does with the derivative. But what I do is I take my a sub n here, I take my factors of x minus c to the power n, and I'm going to add 1 to every power, right? When I take an antiderivative of those x's, the power is increased by 1. I have an n plus 1, and then I have to divide by that new power. Okay? So the derivative and antiderivative are really mostly straightforward. I'm dealing with infinite polynomials here, right? So each term has a really simple derivative and antiderivative. We can generalize that with these two bullets here, with number 1 and number 2. An important thing to note is that the radius of convergence does not change. If I have an initial radius of convergence for my power series, when I take a derivative and antiderivative, the radius of convergence is going to remain the same. However, but the interval of convergence might change. And really what that means is the endpoint convergence might change. So if the radius of convergence stays the same, I'm still taking the center and going out r units. right? I'm still going out r in either direction. However, at the endpoints, we might have convergence or divergence now. It's an interesting thing. So we still have to check our endpoints as something we still have to pay attention to. But the important thing here is it saves us some work. The radius of convergence remains the same. So I don't have to apply the ratio test all over again to find the radius of convergence. I just want to do one example where I take a derivative or antiderivative here and show you kind of some of its use. Write a power series for f of x equals arctan of x. What do I know about arctangent? I know it's derivative. That's an easy one, right? Derivative of arctangent of x is that 1 over 1 plus x squared. And what we notice is this looks very similar to our template 1 over 1 minus x as a power series. Okay, so what we're going to try to do is write this 1 over 1 plus x squared as a power series. And then to get a power series for arctan, all I have to do is undo the derivative. I have to integrate. I have to take an antiderivative. And that should be really straightforward. So I take 1 over 1 plus x squared, and I try to recreate this template here by moving around my denominator a little bit, 1 minus a negative x squared. And of course, that just goes right into my sum as minus x squared to the power n. Okay? What we often do is, again, write this in a slightly simplified form. I have minus 1 to the n out front, and x to the 2n then, right? When I raise a power to a power, I multiply x to the 2n. It's a little bit easier to integrate with this second form here than it is with the first. Okay? So that's why I do this here. And I'll talk about convergence in just a moment. So then arctan is really the integral of 1 over 1 plus x squared, right? That's true. Arctan is the integral of that guy. They have that inverse relationship, derivative and integral. That means that I'm taking c plus the integral of this power series. You won't very often find this notation, right, where I have an integral and then a series inside, but just for the sake of things, I think it's useful to see that I'm adding a constant when I integrate plus the integral of this power series. I wanted to take it a step at a time. When I integrate this power series, what I've got is x to the power 2n. That's the power that's going to increase by 1. So my arctangent is then c plus the sum. I increase the power of 2n by 1 and divide by the new power. That's it. That's all I've got. That's all I need to do to find a series for arctangent of x. I use what I know about geometric series, a sum of a convergent geometric series, and I relate that to the derivative of arctangent, undo the derivative by an antiderivative. The only thing we have to be wary about is when this series converges. Okay? The original series, 1 over 1 plus x squared as a series, has convergence when minus x squared is less than 1. That radius of convergence is going to stay the same. Yeah? When I take a derivative or antiderivative, the radius of convergence stays. So because minus x squared to the power n is geometric, right? I can very quickly find that radius of convergence. And that applies then directly to the antiderivative. Radius of convergence stays the same. The center is 0. I didn't make much mention of that, but it is. So my interval of convergence is from minus 1 to 1, but we would definitely need to check the endpoints. Okay? I'm not going to take the time to do that here. Just kind of, you can look back through the notes. You can plug in minus 1 and 1 for x and determine if that series converges or not. It's a fun exercise to go through. But the radius stays the same. All we would have to check is then the endpoints. Okay? Almost done here. That's really the only example I wanted to do with this. Just kind of give a little crash course of information. I know it's a lot to cover, these two videos here. What we've got is a a way to write rational functions as power series using what we know about the sum of a convergent geometric series. But that's rather limiting. So what we say, finding power series using the template there for geometric series is rather limiting, right? It only gives us so many functions that we can use. Next, what we'll do is we'll develop a technique to find power series for, find a power series representation, rather, for other non-rational functions, okay? Think of things like e to the x, sine of x, cosine of x, and say maybe natural log. These are really the things that we're going to be interested in here, because writing polynomials and rational functions as power series isn't all that exciting, but taking something that we can't write as just x's or a string of x's and writing it as so might be a beneficial thing, and in fact is a beneficial thing. So what we'll look at next in the next kind of 2 sections here, hopefully another video or two, that'll be it, is how to write these, what we'll call transcendental functions, as power series. And there's a whole kind of side of mathematics dedicated towards that. We're just going to tiptoe in there, and that'll be it for the semester. Thanks for watching.